Today we're going to learn about the Bussmann series available fault current calculator, or FC2. I am at the Bussmann division website, which is eaton.com/Bussmann series. And if you go to the upper right corner, you can click in the Google search box, and if you type FC2 and press enter at the top, your first result will give you this little yellow thumbnail. And if you click the link, it'll take you over to the FC2 page. This is for calculating available fault current. And as you scroll down, you can use this tool right off the website. It's a free tool. Or it's also available for Android and iOS. It looks exactly the same as we have it on the website. If it's your first time using it, you'll have a short registration page here. This is just to get your name and your company and your email address, and then it'll give you access thereafter, so you don't have to do that every time. So today what we're going to do is we're going to model a system with a large transformer that's coming into the building, and it has a 4160 volt primary, 3-phase, and a 480 volt 3-phase secondary. It's a 2000 kVA transformer that is 5.25% impedance. And after the transformer, we're going to first determine the fault current at the secondary of the transformer, right immediately at the terminals. And then we will take a 175-foot run of 500 MCM cable, and we're going to use 6 per phase to get down to a distribution panel. And then we're going to calculate what the fault current is at that distribution panel. So to get started, you want to select your system type. We'll go ahead and hit 3-phase here. And then we click Add to System. And then you have a few choices here. You can add a transformer, a conductor run, or a bus run. If you have a known fault current, let's say the utility provides you the known fault current on the secondary of this transformer, you wouldn't necessarily need to calculate the transformer. You've already been given that number. So you could actually start with a conductor run and a known fault current. But in this example, we'll just assume we don't know that, and we were not given those numbers. So we're going to go ahead and add a transformer to the system. If you do know the available primary fault current that is leading into the building, perhaps the utility gave that number, you could add that. If you don't, you can assume infinite. We're going to go ahead and assume infinite current on the primary. The reason we can do that is the transformer only has so much capacity to it, and therefore it can only put out so much fault current on its secondary. So if you know the voltage, the number of phases, and the kVA, and the impedance of the transformer, these are known quantities on the secondary. So the secondary can be just figured out in a worst case fashion. So we're going to go ahead and do that. We'll say no, assume infinite current on the primary. And now we can start entering some of the critical information that we need. So these are necessary to enter. Transformer kVA we said was 2000. The secondary voltage line to line. So even if you had a line to neutral situation at 277, then your line to line voltage in this case is 480. All right, your impedance is 5.25. The percent Z tolerance here on the bottom is a little bit of an adjustment. You can, if you're absolutely certain that it's 5.25% and there is no tolerance that's precisely given to you, then you could actually hit the 0% no change, but we're going to put a minus 10%, which is going to provide the max fault current in this case. What that's going to allow for is just a tolerance again on that impedance, and if it's a lower impedance, you're going to get a higher fault current. So we're going to go ahead and assume worst case. I'm going to add the system. It's going to ask us if we want to add motor contribution. You can do that. You can do it in one of a couple ways. You can add either your full load amps if you know that, or you can add it as a percentage of the kVA. Some people like to just do it that way. So in this example, we're not going to actually add any motor contribution, just to sort of show you cleanly what the transformer will put out until it gets up to the board. So we'll say no. And we've been given, as I scroll down here, we've been given a little graphic, and you see the red X. So the fault X1 shows the total fault current at 50,914 amps. And that is at 480 line to line. And that is our first fault current that's right at the terminals. So that is without having added any conductor run or any other adjustment here. Again, we're going to go ahead and add to the system again. This is going to account for the conductor run. So we want to now add a conductor run to the system. We can also go back and add the motor contribution at this point, but we are going to decline to do that at this point. So let's go and add the conductor run to the system. So the length of the run, we said that was 175 feet. It is 6 conductors per phase. It's a pretty hefty system. The conductor size, we said was 500 kc mil. We just have to get down to the bottom of the list here. 500 kc mil. And then you have your choices for copper or aluminum conductor. If you were running 3 single conductors, or if it were a jacketed cable, a 3-conductor cable, you would select on this box here on the right. And then the conduit type we're going to assume is steel rather than PVC, which would be non-magnetic. And then we go ahead now and add that to the system. And of course we still have the first fault we were given here. And as we scroll down a little bit, we see another X. We're given fault X2, and we are now running at 41,011 amps of available short circuit current. That's 175 feet away from the secondary of the transformer. So if you had a distribution panel or switchboard, what have you, at that point you would have to have a short circuit current rating that was greater than this value in order to be a suitable installation. So National Electrical Code provides for the fact that you have to have a correct and proper short circuit current rating on your equipment. And this is a way to find out how much short circuit current you have so that you know how you need to build that or how you need to specify it. In addition to that, 110.24 out of the National Electrical Code provides for marking requirements, and in this case we can actually create a label. So if you wanted to create a label at this point 175 feet away, you can go ahead and do that. You would basically enter your information here, put your email address, you could enter a project name, you can edit in here, you can say distribution panel, let's just say we'll call it PDP, the label size, and the format you want to receive it in, if it's PDF or what have you. So we'll say project name, we'll just call it distribution panel. Email, I'm going to put fusetech@eaton.com. So this will actually go ahead and in a few minutes it'll email over to the specified email that you have. It's really handy if you have a smartphone in the field and you want to get your hands on the label and see what it looks like quickly. You can have it go ahead and send it to you kind of while you're waiting there, as long as you're out there looking for it. So we're gonna keep these 4x6 just to show you some of the other selections we have. You can do multiple different sizes here. We'll keep it 4x6 for now, and then we'll go ahead and say send label. There we go. So it's gone ahead and set up to send the label over to that email address. You can go ahead and view the label. So let's go ahead and look at what it looks like right now. And it is actually right here. Go ahead and straighten that out. And there it is. What you have is tells you it came from FC2 available fault current calculator. This was again our project name. We call it distribution panel. Fault name PDP. Is a 3-phase system. 41,011 amps available fault current at this point. This is again the X2 point. We could have left X2 in there if we wanted to. It is 480 volts line to line. Calculation was performed August 25th at 10:42 p.m. And so this is suitable for printing and inserting on the system. We go ahead and close that out. You can also go back to the system diagram. There's other things you can do. You can also, like we said, add motor contribution in. So there's other factors. You can add another conductor run beyond that if you like. Or if you had a bus run, for example. So you can actually model your system from the transformer if you have that information, and all the way down to different distribution panels and sub-panels beyond that. So the purpose, again, very critical to know the available fault current at your equipment, and this tool is very handy and helps you do that.